Okay, hello everyone. Welcome to one more video. This is the second part on differentials, and in the previous video we have introduced the concepts and gave some important comments and notes on what differentials are. And in this video we want to see how differentials are applied to some problems. Now we have seen an important fact that is that in general differential of a function is not the same as the increment of the function. However, we will see that even though dy is different from delta y, that is, differential is different from the increment, dy is a good approximation to the increment given that the absolute value of the differential of x, which is the increment of x, is, this is important, sufficiently small. So the differential has that feature that it is a good approximation under the condition that dx is sufficiently small. Now, let us see why actually that works. So, what we want to see is why is dy good approximation? Well, when we have approximation, we deal usually with limits. So let us see how we can. Basically, what we will prove is that limit when delta x or the differential goes to 0, the increment of minus f prime of x, we want to show that this is 0. That means that this is a good approximation. Well, we have limit delta x minus f prime of x equals. Now both of these limits exist. So limit when delta x goes to 0, delta y over delta x minus limit, this is just formally here because f prime of x is just a constant, and we have here that this is f prime of x and this is just f prime of x as well, and that is 0. When the limit, so let us call this 1. So 1 means that dy dx minus f prime of x can be made as close as possible to the 0 whenever dx is close to 0. So that's actually the meaning of this. Maybe I'll just put like, that's just a paraphrase. So if you want, okay. Or using epsilon delta, so using epsilon delta, so epsilon for every epsilon greater than 0 there is delta greater than 0, so that dy or dx minus f prime of x of delta y, over delta x, if delta x by absolute value less than delta. That is, now this is equivalent to delta y minus f prime of x. We just rewrite that if, or using the definition, I'll just see, okay, I'll use the same color, f prime of x less than epsilon, no, sorry, dx if less than delta. This here means that dx, so this here means actually dx is very small, because we assume that dx is less than delta, and that is much less than 0. So what we have is that if dx is very small, then the increment is, and we can even use the dx itself. So there is some number epsilon, so for some epsilon greater than 0, and this dx also depends on this epsilon, basically. Why? Because of this, because for every, so whenever we fix, so having epsilon greater than 0 fixed, there is delta depending on that particular, let's just put star here, on that epsilon star, and then everything else, so that dx less than delta implies the increment of the function, or the distance between the increment is less than that epsilon star times dx. And this again, this is some delta of epsilon, so depends on epsilon output star. That's maybe not less important, but what is truly important here is to understand or to rephrase this. So I will just copy this and I will put it here so we have that, and even this I don't really need, because when it comes to understanding, so this actually means if dx is very small, okay, then this is, when you read this is the absolute value of the difference. That actually means the distance between dy and f prime of x is very small. Okay, but what does that mean? That means exactly what we want. F prime of x is good approximation of, or sorry, yeah, of delta y. And this is, we can say, or if we just go back, that means that dy, which is f prime of x dx, is a good approximation to dy. Okay, so this is all the answer to the question why, how the differentials are used, and also why are they good approximations. So here is basically the proof or the derivation of the fact that indeed the distance between the increment of the function and its derivative are closely related to each other. Let's see one small just example to see how is this used. Example 1. If y equals 1 over x squared plus 5 increases, that is the function, and x increases from x equals to 2, x equals 2.04. Find the approximate change in y. Now you can see that dx, okay, you can pause the video if you want and you can try. I'll write here the solution. Okay, so you can see that dx is 2.04 minus 2, which is 0.04. So this is very small. So you can see that actually we want this. Dx is very small. So what do we need? Well, if we have y, so we want dy, which is f prime of x times dx, okay? And dy is minus 1/2 x squared plus 5 to the power minus 3 over 2 times 2x dx, which we can write as minus x squared plus 5 3 over 2 times dx. And now we have, you see, we have here, remember what we have said. This is why it is important to have said that before. dy is the function of x and dx, and we have here x and dx. So x is 2, dx is 2.04. Dx, sorry, is 0.04. Apologize. 0.04. And you can see that here comes. So what we want is actually to evaluate dy at 2 and 0.04. And that now we use here. So that is minus 2 over 2 squared plus 5, and then 32, 3 over 2, and then times 0.04. So I will just use here. So this is, see, this is x, and this is dx. And if you calculate that, that is minus 0.00296. So the approximate, hence the approximate, so dy is approximately the same as dy, and that is minus 0.00296. And that is the example how to use the differentials. Thank you.